In this video, I will discuss some NEET PYQs from the topic fluid dynamics. These questions are based on Toricelli's law, Stokes' law, and terminal velocity. Torricelli law gives the velocity of the fluid that's coming out of a huge container, and there is a small opening at the bottom. Let me consider water, and there is an opening here, so the water will come out. Let the velocity here be v2, and the velocity here be v1. The cross section of this opening here a2, and this cross section here a1. And let me assume water, incompressible fluid. So the continuity equation rho AV is constant, but since here rho is constant, A into V is constant. So for incompressible fluid, continuity equation takes this form A1 V1 equal to A2 V2. V is the velocity. This is like an overhead tank, and there's a small opening like a tap. So in this particular situation, we have this condition. This A1 is much greater than A2. There is a small opening, and this is a huge tank. So from this, I'll get V1 equal to A2 by E1 into V2. So this is approximately 0 because A2 is much smaller compared to E1. So this is a very small quantity. So we can make this approximation that the velocity with which the level of this water is dropping down, it's almost 0. Here the water is coming out. So this is one thing. After that, you can use Bernoulli equation to write the energy of a fluid element here and here. So energy is pressure energy P1 plus kinetic energy here half rho 1 V1 square plus gravitational potential at this point mgh, which will become rho gh at point 1. That should be equal to the quantity set 2 P2 plus half rho 2 V2 square plus rho 2 GH2. This is open to atmosphere, so P1 is atmospheric pressure. This is also open to atmosphere, so P2 is atmospheric pressure. So both are equal. So these two will cancel. Pressure will cancel. And then we have this velocity, which the level is dropping down. It's almost 0. So this term is 0. Because velocity is 0. So this term will go. So from this I can get V2. And also let me assume it's an incompressible fluid like water. So density is same. So density will cancel. So half V2 square G H1 minus H2. So see, Earth's surface is here. This is the height H1. And at this level, the height is say H2. Let me call this difference H1 minus H2 as capital H. So from this I get the result. Velocity with the water is coming out of the tap at the bottom is 2gh square root. So this is Toricelli's law. One way to remember this result is take a small fluid element here. So you have some mass. When it comes out here, it have a velocity. Here the velocity is 0 because here the level which is there, speed is the level is dropping down is very small. So the energy here is potential energy mgh compared to this level. If you assume this as reference, then energy is mgh. They will get converted as kinetic energy at this point, half m v2 square. Potential energy here is 0 because I am assuming this as reference. So with this as a reference, the potential energy at this point is mgh. So from this I get this result. So this is one way to remember this velocity. Next is Stokes' law. So consider a solid sphere is it's moving inside a liquid. The density of the solid is more compared to the liquid, so it will move down. Let it move with the velocity v. There is a friction between two solid surfaces. Similarly, there can be a friction between solid surface and a liquid surface. So this friction will give a force which will oppose its motion. So it will be in the upward direction. This is the viscous force. Let me call it Fv. So this viscous force, we can expect it to be more if the sphere is bigger. Bigger sphere means large contact area, so the viscous force will be more. So if the radius of the sphere is say r, then the viscous force is proportional to r. Also, the thing is moving with a larger velocity, then the drag force will be more. So it's proportional to the velocity which the sphere is moving. And if the liquid is thick, then the viscous force will be more. So it's proportional to the viscosity of the fluid, which is eta. Like a thick liquid like honey or castor oil will have more viscosity compared to thin liquid like water. So that's viscous force depends on the liquid also, viscosity of the liquid. So this thing can be combined and written as the viscous force is proportional to RV eta, and this constant of proportionality is 6 pi. So 6 pi eta R, this is the viscous force. So this was founded by Stokes, so it's called Stokes' law. And as it keeps moving down, the velocity will keep on increasing because there is a force downwards. But as the velocity keeps increasing, the viscous force will increase. So at some stage, it will saturate, or the velocity will saturate. So the force acting on the sphere is, one is the weight of the sphere, mg, and upward force is the viscous force, which is slowing it down. Another force there is there, which is the buoyancy force. An object inverts inside the liquid will have a extreme upward buoyancy force. So initially, when this velocity is less, this will be small. So this will dominate. So there will be net downward force. So as the thing keeps on increasing, this Fe value will increase because this viscous force is proportional to velocity. So at some stage, Fe plus Fb will balance this mg. After that, the net force is zero, so it will move with a constant velocity. So that velocity at which this balance is happening is the terminal velocity. So to get the terminal velocity, I have to put the buoyancy force plus the viscous force will be equal to mg. Less than this terminal velocity, mg will be more, so it will keep accelerating downwards. So at a particular velocity, this will be balanced. Buoyancy force is the mass of the liquid that's being displaced. That's volume of the sphere into density of the liquid. Liquid have density rho L, and this solid sphere has got a density rho S. So this is mass of the liquid displaced into G, which is the weight of the liquid displaced, plus viscous force 6 pi eta R V. And mass of the sphere is volume of the sphere V into density of the sphere into G. And this speed at which this balance is there is the terminal speed. So from this I get the expression for the terminal velocity. So with this theoretical background, you can solve this NEET PYQs. I'll discuss a couple of questions. This is the first one. A small hole of area cross section 2 mm square is present near the bottom of a fully filled open tank of height 2 meters. Take G equal to 10 meter per second square. The rate of flow of water through the open hole would be nearly. You can pause and run this question. Open tank. There's a small hole here. Cross section area 2 millimeters square. The tank height is 2 meters. The height of the water is 2 meters. G is 10. So you have to find the velocity with which it's coming out. So this Toricelli's law. Velocity is square root of 2gh. The way to remember this formula is take a small fluid element here of mass m. So the energy here is mgh, because this is almost at rest, because this is a huge area compared to this area. So the velocity which the level is dropping down is very, very small. It's almost zero. So only potential energy is there, which is mgh. So mgh, when it comes here, it becomes kinetic energy half m v square, because I'm taking this as reference for the potential energy. So mg is going to convert to half m v square. So m will get cancelled, so you get this formula. Put the values given. 2 into 10 into height is 2. Square root of this one. So this 2 root 10. This is the velocity, SI units, meter per second. You have to find the flow rate. Flow rate is nothing but the volume of liquid that's coming out. That will be meter cube per second. How much of volume is coming out in 1 second? So this is nothing but the volume flow rate, which is A into V. Mass flow rate is rho AV, because volume flow rate density is the mass flow rate. Volume flow rate is A into V. So volume flow rate Q is cross section area is 2 mm square. In SI units become 10 to the minus 3 square. Millimeter to meter 10 to the minus 3. It's mm square. To meter square is 10 to the minus 3 whole square. So this into 2 root 10. So 4 into 10 to the minus 6 into root 10. 10 to the minus 6 factor is there. So 4 root 10. Root 10 is approximately 3, little bit more than 3. Square root of 9 is 3. So this 9 plus something. So it is 12 into 10 to the minus 6. So option A. Square root of 10, you can write as 9 plus 1 square root. So 9, if it comes, will become 3 into square root of 1 plus 1 by 9. So binomial approximation, if you do, it will become 3 into 1 plus half into 1 by 9. So it's approximately 3. So this is approximately 12. D is the correct answer. This is what is done here. Next question. A small sphere of radius small r falls from rest in a viscous liquid. As a result, heat is produced due to the viscous force. The rate of production of heat when the sphere attains a terminal velocity is proportional to. You can pause and run this question. So solid sphere falling in a liquid. This liquid, there is a solid sphere of radius r. It's a viscous liquid. So there will be a viscous force which is given by Stokes' law. 6 pi eta rho p, where r is the radius of the sphere and v is the velocity, and it moves with the terminal velocity. So this is vt. To get the terminal velocity, when it attains terminal velocity, there will be force balance. mg will be balanced by the buoyancy force plus the viscous force. From this, I'll get the terminal velocity. Mass of the sphere is volume of the sphere, the density of the sphere into g. Buoyancy force is the weight of the liquid displaced. Let's equal to the volume of the sphere into density of the liquid. And the viscous force is given by this. This is the terminal velocity. So this volume is 4 by 3 pi r cube. The density of solid minus density of liquid into G equal to so all these things are fixed. Solid density is fixed, liquid density is fixed. So the terminal velocity Vt is proportional to r square. R square into some constants. Okay. So Vt is proportional to r square. This here there is an r. So viscous force is proportional to this is viscous force. So what you have to find is the rate of production of heat. So viscous force is proportional to r cube, and rate of heat production dH by dt is the work done per unit time. So viscous force work done is F into the displacement by dt. This is actually the velocity. So F into velocity. Here the velocity is the terminal velocity, and the terminal velocity is proportional to r square. So this is proportional to r cube, the viscous force, and this terminal velocity Vt is proportional to r square. So the total dependence will be r h to the power 5. Work done is F dot S, power will be by dt, so F dot V. So the rate will be the heat energy is dissipated, same as the heat power, which is F dot V. So F into V, F is the viscous force, 6 by eta Rv, and V is, so it's proportional to R into V square, and the terminal velocity V is proportional to R square. So the total dependence will be proportional to R h to the power 5.